Before we start, can people hear me? Okay, just while we're waiting, can people hear me? Yeah, cool. All right. I guess we'll just get started then. So, welcome to the second half of Math3711 slash 5706. So, today we'll be covering the rest of the course. So, we'll be covering rings, domains, and fields. Yeah. So, let's get started. So, I guess like sort of an introduction to a ring. So, you've sort of looked at groups, all right, in the previous part. So, you've looked at what a group is. What we're going to be doing is we're going to be looking at an additive group. And then what we're going to be doing is we're going to be adding on an extra operation. So we're going to be adding on the operation of multiplication. And then once we have that, then we have a ring. Cool. So formally speaking, we define a ring to be a set R that is equipped with two operations, where it's equipped with an additive operation and a multiplicative operation, and it satisfies the following properties. So for addition, we require that R is an abelian group. So from our characterization of groups, we require R to be closed under addition. We require R to be associative under addition. It requires the additive identity element, and every element must have an additive inverse. So that's enough for R to be an additive group. But we also require R to be abelian, meaning that it requires the commutative property as well. It can't be said the same for multiplication though. Multiplication is a little bit less strict. So for multiplication, all we require is closure and associativity. And this is enough for you to define a multiplication operation. And then these two things are linked pretty nicely under the distributive property. So if you take two elements and you add them together and you multiply by some other element, then you also have that it's the same thing as A times C plus B times C. And similarly, if you do the multiplication operation first, then you have that it's A times B plus A times C. So these properties or these axioms are enough to define a new algebraic structure that has two operations. So naturally now, let's sort of talk about a smaller type of ring. So let's consider a subgroup of a ring. And this subgroup is not necessarily a subring because the ring itself doesn't necessarily have a multiplicative identity. So it's not necessarily a ring in its own right. But we're going to look at the additive subgroup instead. And the question here is, well, given this additive subgroup, what sort of properties should I impose on this subgroup so that when I take the quotient, I still form a ring? And this will lend itself nicely to the definition of an ideal. So before we even talk about ideals, let's sort of talk about the motivations behind why we define an ideal in this way. So the first thing to notice is that when you're considering the quotient, remember that I is an additive subgroup. So I'll highlight that. So I is an additive subgroup. So if you require, so remember way back when we touched on groups, the cosets that we define on the additive subgroups come in the form R plus I, where I is your subgroup. And this has to hold for every representative R. So R here is a representative for our ring. And what we're going to be looking at is what happens when you take R plus the entire subgroup itself. So remember that this comes in this set here, where you take R plus I for I in the ideal, or in the subgroup I. Now, we're going to impose some conditions on multiplication for it to make sense. So if you take two cosets and you multiply them together, you should get another coset in this form here. So you take a representative of R, which is A, you take a representative of R again in the form of B, and you consider what happens when you multiply these two cosets together. And from group theory, you should end up with another group, or you should end up with another coset. And the representative is given by the product of the two representatives that you started off with. And this has to hold for every representative in R. So when you FOIL it out, when you do the multiplication itself, you obtain this result here. And one thing you notice is that AB and AB are already here, which is good. I times I prime, remember that I and I prime are elements in I. That's already an element of I. So for this equivalence to hold, we require both of these elements to be inside I. And this is going to be the motivation that we're going to impose to define an ideal. And so for our subgroup to generate the quotient ring, we do require this condition here. And this is how we define an ideal. So let's have a look at the definition of an ideal. So take a ring R, take an arbitrary ring R, and we're going to define the subgroup as follows. So I, under the addition operation, is actually an additive, is an abelian subgroup. So I plus is an abelian group, and then for every R in your ring and every X in your ideal, Rx must belong in I and XR must belong in I as well. And if you have these two properties hold, then we call it an ideal. And so what you can notice is that the ideals operate really closely to normal subgroups, right? If you take a group G, so if I consider a group G and I decide to take the quotient of a normal subgroup, you end up with, so this forms a group. In a very similar vein, if you take a ring and you quotient it out by an ideal, you form a ring. So we also define the ideal notation by the same notation as we use for normal subgroups. And so it might be confusing because we're using the same notation for two different things, but we're looking at ring structures and we're looking at group structures. So the context of this notation should be clear. So one further thing that we might notice is that I itself may not necessarily be a subring because 1 is not required to be in a ring. Right? So you don't require the multiplicative identity to belong in your ring, and therefore I may not even be a subring at all. And it actually turns out that if 1 remains in I, so if 1 is an element of I, then what we actually get is that 1 generates the entire ring because every element in your ring can be generated by your identity element. And therefore, if 1 belongs in your ideal, then the ideal is precisely R. So this is a fairly important point, and this is something that we're going to come back to when we're doing examples of ideals as well. Cool. All right. So let's have a look at an example, and we're going to prove that this is an ideal. So let's take an ideal I, and let's take an ideal J over a ring R, and then we want to prove that if you take the sum, or if you take the sum of two ideals, you actually get an ideal. And then we want to determine if we take the product of two elements in your ideals, we want to determine whether that is actually an ideal as well. So let's go ahead and do that. So let's prove the first part. So we want to take I and J. So both of these are ideals inside your ring R. And what we're going to do is we're going to consider I plus J. And that's going to be the set of elements where I belongs in I and J belongs in J. And we want to prove that this is indeed an ideal. So I'm going to just leave the abelian part to you guys, but it's not too hard to show that if you take I plus J under the additive operation, you actually get an abelian group. But let's have a look at the more interesting part. So let's take an element. So what we're going to do now is we're going to prove that if you take an element A in your ring R, you take an element in I plus J, then what happens is that AX is in I plus J, and XA is also in I plus J. So to do this, let's take an element in your ring, and we're going to take let's also take x in I and y in j, so that x plus y belongs in I plus j. So x plus y is just some arbitrary element inside I plus j. So let's have a look and see what happens when we take the product of these two things. So a times x plus y is just ax plus ay. But notice that I is an ideal, right? And x belongs in I. A belongs in the ring. Because I is an ideal, this has to belong in I. In the same vein, this belongs in J. This belongs in your ring R. So altogether here, this has to belong in J. So now this has to be an element in I, this is an element in J, and so therefore the entire thing here belongs in I plus J. So this is just an element in I, this is just an element in J. By definition, this has to belong in the set I plus J. And you can do the same thing with the reverse. So what we're going to do is we're going to also take x plus y times a, but that's just xa plus ya. And again, remember that I and j are ideals in your ring. So this portion here belongs in I. This portion here belongs in j. So the entire thing here has to belong in I plus j, noting that I and j are ideals in your ring R. And so we've proven the second axiom, and the first axiom is not too hard to see. So therefore, what we can conclude is that I plus j is an ideal of R. Cool. So it's just checking the first and second axioms of your ideal, of the definition of the ideal. And then once you know that I and j are ideals of your ring R, then the result actually follows really nicely. So let's have a look at the second question now. So we're considering the set K, where it's going to be xy, where x comes from I and y comes from j. And we're going to determine, so is this an ideal? So the answer is no. So this is actually not an ideal. And to show this, let's have a look at an example. So we're going to consider the ring. So consider the ring. We're going to consider the ring of polynomials with integer coefficients. And let I equal to the following ideal. So we're going to consider 2x. And j is going to be the ideal generated by 5 and x. One thing we notice with these two is that x doesn't belong in K. This might not be obvious at first, but what we notice is that you can never generate x out of a product of these two things, right? So if you take an element in I, so let's just take, if you take 2, and then you take x here, you can generate 2x. You can generate things like 5x. You can generate 10, etc., etc. But you can never generate 2x. You can never generate x out of a product of this and this. So as a result, we know that x cannot belong in your ideal. So if this was an ideal, we know that x can't belong in K. But what we know is that if K was an ideal, so if K was an ideal, then, well, what we can do is we can generate 5x minus 2 times 2x. So remember that if k was an ideal, then it's an additive, it's an abelian group under addition. So we can generate 2x, implying that we can generate things like minus 2x, which means that we can generate something like minus 2 times 2x. And we know that we can already generate 5x. So because it's an additive, or it's an abelian group under addition, we know that this has to hold as well. And if you simplify this, you end up getting that x has to belong in k. But we noted that x can't belong in k because there is no element in here and here that when you take the product, you end up with x. So hence, we hit a contradiction. Right? So there's, if it was an ideal, then we can generate x. But we know that x can't belong in k because there is no possible way to generate x out of a product of elements in these two things. And therefore, k is not an ideal. Cool. All right, let's go back to the slides. Yeah, and I'll have the solutions here as well, so you can cross-check as well. Cool. All right, so let's do another example. So this time we're given that R is a commutative ring. So something that we want to clarify is that R is a commutative ring. So that means that under the multiplication operation, the elements commute. And we want to consider I to be this set. And we want to prove that I is an ideal. So let's do that. So, okay. So R is a commutative ring. And we want to consider I to be the set x in R, where x to the n equals to 0 for some n in n. Okay, and we want to prove that this is an ideal. So again, you need to satisfy two axioms here. So you want to show that I under the addition operation is an abelian group. So you just have to prove, or you just have to show that the axioms of an abelian group are satisfied. So you need to show closure, you need to show inverses exist, you need to show it's commutative, associative, and the identity element exists. The second axiom though is a bit more interesting, so I'll just probably do that instead. So let's consider some elements that we want to take some R in our ring, and we want to consider some X in I. And what we want to show is that Rx belongs in I, and XR belongs in I as well. But we only need to show one side because you have the fact that R is a commutative ring, so you know XR operates the same as Rx anyway. So we'll show Rx is an element in I, and this is not too hard to show because you notice that since X is in I, then X to the power of n equals to 0 for some n in the natural numbers by definition. So what we can do is we can consider Rx to the power of n, and that's just Rx times Rx n times. And because R is a commutative ring, we can swap the order of all of these elements. So what we can do instead is we can group all of the R's together and then group all of the X's together. So what we end up with is R to the power of n times X to the power of n, because R is commutative. Okay, so once we have that, then it's easy to see that this actually just goes to 0. So we have R to the n times 0 because X belongs in I. And so this, as a result, is 0, which implies that Rx must belong in I, and that also implies that XR belongs in I, and that proves that I is an ideal in R. So the key point here is that we required R to be commutative for this to work, because otherwise we can't just swap the order of the elements here. And then once you have that, then everything else falls out pretty easily. Cool. All right. So yeah, these are the solutions. All right, so let's have a look at some properties of ideals. So we sort of talked about the definition of ideals. We also proved some things about ideals. So let's have a look at some other properties of ideals. So if you take a set of ideals, so you consider some number of ideals, the intersection also happens to be an ideal of your ring R. If R is a field, then there are only two ideals, so there are precisely only two ideals. It's the ideal generated by the 0 element and the entire ring. So remember that previously we said that the ideal generating the entire ring is just the identity element of the multiplication. So it's just the ideal generated by the identity elements. And lastly, if you take a subset of your ring R, then you can actually generate S using a finite number of elements and we define it as the intersection of all ideals that contain S. So this is going to become pertinent later on. So we're going to be talking about things like a principal ideal, where this concept comes up again. But the idea is that what we can do is we can look at a subset of S, and we can say, let's consider all of the ideals that contain S, and then what we're going to do is we're going to take the intersection of all of them, and then what we get in the end is precisely the ideal that generates S. So for example, if I consider the ring Z, and then I consider all of the elements. Let's just say 2, 4, 6. So if we consider all of the ideals generated by, okay, so what we can do is we can consider elements generated by 2, 4, 6, 8, etc. What we can do is we can look at the ideal generated by 2, and then the intersection of all of these generates 2, 4, 6, 8, and also the negative parts as well. So we can talk about finitely generated ideals, and that's just ideals generated by a finite number of elements. Okay, so this is actually a really nice segue, because we can start talking about things like principal ideals now. So in the previous point, we talked about ideals that can be generated by finitely many elements, and then we can express this as an ideal generated by alpha 1, alpha 2, and alpha n. And then we take the intersection of all of these. And then it's going to be precisely the ideal generated by every single one of these elements here. We call I a principal ideal if it can be generated by one element. So for example, if we looked at the ring of integers, we can look at, say, 2, which generates something like 2, 4, 6, 8. So it's going to be the set of elements which are precisely the even numbers. Oops. And also we'll have the negative counterparts as well. Likewise, if we consider the ideal generated by 3, it's just going to be all multiples of 3 as well. 3, 6, 3, 6, 9, 12, etc. So we can talk about ideals generated by a single element in this way, and we call it a principal ideal. Okay, so let's have a look at an example. So what we're going to do is we're going to show that this ideal generated by 3 and this polynomial is not principal. So let's do that. Okay, let me just do it here. So let's consider the ideal generated by 3 and x cubed minus x squared plus 2x minus 1. And then we're going to look at this ideal over the ring of polynomials with integer coefficients. So let's just suppose, so remember that if this was principal, then there is an element in this ring such that it generates 3 and it generates this polynomial here. So suppose that, let's call this I. Suppose that I was principal. Then what we can do is we can construct an element alpha. So then there exists some element. There exists some element alpha that belongs in your ring, such that when you consider the ideal generated by alpha, it is precisely the same as the ideal generated by 3 and the ideal generated by the polynomial here. So let's take a look at this. So if alpha generates 3, that means that alpha must divide 3, because the only way for you to generate 3 is to look at all multiples of 3. But at the same time, it also has to divide this polynomial here. So let's have a look at this first divisor here. So if alpha divides 3, then we really confine alpha to a small set of numbers that are possible. So it could be plus or minus 1 or plus or minus 3. These are the only possibilities for alpha. So let's have a look at each one of these when we are looking at alpha dividing this polynomial here. So we can see that if this is the case, so if alpha is either going to be minus 3 or 3, then what we can note is that alpha doesn't divide this polynomial. And the reason for this is because if we consider some polynomial where you take a 3 out, clearly the polynomial must be degree 3. And moreover, the leading term must be 1 over 3. So if there was a polynomial that divides 3, then we know that the leading term must be 1 over 3, because there can never be a case where we reach a coefficient of 1, unless the leading coefficient was 1 over 3. So we know that if alpha was either minus 3 or 3, then alpha cannot divide this polynomial. But that leads to a contradiction. So it must be the case that alpha must be either minus 1 or 1. But if alpha is 1, if alpha were to be either minus 1 or 1, then what we can see is that the ideal generated by alpha is precisely going to be the entire ring, right? Because when we consider the ideal generated by -1, then clearly the element 1 must also belong in the ideal. But at the same time, if 1 belongs in the ideal, then the ideal generated by alpha must be the entire ring. And what we're going to do is we're going to show that this can't be possible. So if it was possible, then X must belong in the ideal generated by alpha, because this generates all of ZX. So it has to generate X as well. And what that implies is that X must belong in the ideal generated by 3 at x cubed minus x squared plus 2x minus 1. But this is not possible either, right? Because there is no way to generate x by itself. And so therefore we hit a contradiction here. And thus, this ideal, I think I called it I, so let's call it I again. But thus I is not principal. So to summarize, what we can do to show that something is not principal is to show that, or to suppose that it was principal and we hit a contradiction. So the only way for this to happen is if I was not principal to begin with. Cool. All right. We'll go back to the slides. Yeah, so I've written out the solution here. All right, so once we talk about principal ideals, we can start talking about other types of ideals as well. So the second ideal that we might like to talk about is a maximal ideal. So a way to kind of think about this is if I consider I to be maximal, then there is no other way to fit an ideal between I and R without the ideal being exactly I or R. So if I had an ideal that was a bit bigger than I, not R, it was J. So if I had another ideal that was bigger than I, but smaller than the entire ring, then it must be the case that J is either going to be I or it's going to be R, right? And as a result, I is maximal over all ideals that are not precisely the entire ring. So that's a way to kind of think about maximal ideals. And the formal definition here is as follows. So we call an ideal a maximal ideal if it is maximal among ideals not equal to R. In other words, if you take another ideal J, and J includes I, but J is not the entire ring, then it must be the case that J is equal to I or J equals to R, right? There is no other way to get an ideal J between I and R. And so one thing that we can talk about is the quotient ring with a maximal ideal. So if we consider the quotient ring with a maximal ideal, it turns out that the entire field, or the entire ring, or the quotient ring itself, is actually a field. So one thing you can note here is that if you take a polynomial P, or if you take an element P, you consider the ideal generated by it to be maximal. So if this is maximal, then what that implies is that P is irreducible as well. And so as a result, when you take the quotient with something that's irreducible, you get precisely a field. And this is just another characterization of a field that we'll talk about later on as well. Cool. Okay, so let's have a look at the last type of ideal that we're going to be talking about in this course. So let R be a commutative ring. So this time we're going to be looking at a commutative ring rather than just a ring. And we're going to consider an ideal that is not R. So we're not going to consider the entire ring, but we're going to consider a portion of the ring. And we say that I is a prime ideal if you take the product of two elements inside your ring being in I, implying that R is in I or S is in I. So a way to kind of think about this, right, is to look at prime numbers. So if you take a prime, so P prime, and you know that it divides AB, then it implies that P divides A or P divides B. Analogously, this is very similar to saying this as well. So if RS belongs in I, what that gives you is that R must belong in I or S belongs in I. And then we call I a prime ideal. So it turns out that every maximal ideal is a prime ideal, but the converse is not necessarily true. So every maximal ideal is prime, but not all prime ideals are maximal ideals. So if you want to show that something is prime, it's enough to show that it's maximal, and the maximal ideal consequently implies that it's also a prime ideal. So we're going to use this characterization to prove that this ideal is a prime ideal. So let's do this. All right. Okay. So let's go ahead and do this. So we're going to consider the ideal that's generated by 2 and 1 plus the square root of minus 5. And we're going to consider it over this ring here. Okay. So the first thing we notice here is that we can actually write this in another way here. So notice that the minimal polynomial of square root of minus 5 is x squared plus 5. So what we can note here is that we can generate an isomorphism from z of square root of minus 5 to the following ring. So what we can do is we can generate an isomorphism from z of square root of minus 5 to z of x, so the set of the ring of polynomials with integer coefficients, quotient x squared plus 5. And so what we can do is we can actually replace square root of minus 5 with x here. And so what we can do is we can look at the quotient. So when we consider the following quotient, this is actually isomorphic to the following. We take 2, 1 plus x. So we're replacing square root of minus 5 with x, and x squared plus 5. Okay. So what we're going to do is we're going to quotient out by 2 to begin with. So what ends up happening is that this is isomorphic to the field of... So we're going to look at Z2. Z2 is precisely a field. And we're going to quotient out by the following here. So this is actually isomorphic to, or it's actually precisely equal to the following here. Right? Because Z2 is precisely F2 as well. So Z2 is a field of 2 elements, and F2 is also a field of 2 elements. And then what we notice is that here, neither of these affect F2 of x in any way. So this is irreducible in F2x. This is also irreducible in F2 of x. So what ends up happening is that this is actually isomorphic to the following. So Actually, no. Yeah, it's actually isomorphic to the field generated by, it's isomorphic to the field of two elements. Yeah. So this is a field, meaning that what we've basically proven is that this ring, this quotient ring, forms a field, or is isomorphic to a field. So this thing here is a field, and what that implies is that 2 and 1 plus square root of minus 5 is actually a maximal ideal. And what that consequently implies is that this ideal is also prime. Cool. So the hard part is figuring out this isomorphism, but you can justify these isomorphisms just by looking at irreducible elements in this ring here. And once you've figured that out, then it's easy to see that it's isomorphic to the field of two elements. And because it's isomorphic to a field, the original quotient ring that we started off with must also be a field, because isomorphisms take fields to fields. And as a result, the ideal that you quotient out by has to be a maximal ideal, and every maximal ideal is a prime ideal. And so you get that this here is a prime ideal as required. Cool. Yeah. So now we can talk about a generalization of the Chinese remainder theorem for rings. So before we even begin talking about Chinese remainder theorem for rings, let's just sort of talk about the Chinese remainder theorem for integers, and then we generalize it to arbitrary rings. So let's take a bunch of positive numbers or positive integers, and these are going to play the role of our modulo, our smaller modulo. And what we're going to do is we're going to suppose that these are co-prime pairs. And once we note that, then we take any integer a1, a2 up to ak, and the Chinese remainder theorem tells us that there is a unique solution. So there is a unique solution to a bunch of simultaneous equations in the smaller modulo. And the unique solution comes in the form n equals to the product of all of the modulars. So this is really useful when you're talking about solving Diophantine equations, putting them into modulo form and noting that each of them are co-prime, meaning that there is a unique solution to this set of simultaneous equations. What we're going to do now is we're going to generalize this to rings. So instead of looking at n1, n2 up to nk, we're going to be looking at ideals of a ring. And instead of looking at co-prime pairs, we're going to be looking at elements where we're going to be taking the sum of two ideals, and that has to generate the entire ring. And then the Chinese remainder theorem holds. So let's just start off with an arbitrary ring, R, and let's consider k ideals. What we're going to do is we're going to suppose that I plus ij equals to the entire ring, and each of the i's is distinct from all of the j's as well. What we're going to do is we're going to consider the intersection of all of these ideals, which we've sort of stated that was also an ideal. So the intersection of ideals is also an ideal. The Chinese remainder theorem states that we have an isomorphism from I to the product of quotient rings. So in this example, what we can do is we can look at Z mod 12, and this is isomorphic to Z mod 3 cross Z mod 4. So instead of looking at solutions to the mod 12 equation, we can look at solutions to mod 3 and solutions to mod 4 instead. So something that might be confusing, and I think it was confusing for me when I first learned this, is what this actually means. So another way of looking at, this thing here is to go, okay, well, is there an element I? So is there an element I in I and an element in J in IJ such that the sum of these add up to 1, which is the multiplicative identity. And recall that if that is the case, then remember that the sum of ideals is an ideal. And if that is the case, then the ideal generated by 1 generates the entire ring. Cool. So let's prove, let's have a look at this question. So we've given M1 is not equal to M2, and these are two maximal ideals. And we want to consider the intersection of these two ideals, and we want to prove that R mod I is isomorphic to a direct sum of two fields. So one key takeaway here is that we want to prove that this is isomorphic to a direct sum of two fields. And we're given that these are two maximal ideals. So naturally, what you might want to look at is looking at R mod I, R mod M1 and M2. M1 and R mod M2. And remember that these two will form fields. So that's what we're going to be looking at when we're doing the proof. So let's bring this up. So we're going to let M1 not equal to M2 be maximal ideals. Alright, so what we're going to do is we're going to first of all notice that M1 is inside the ideal generated by M1 plus M2, and that's also inside R. Similarly, you know that M2 is contained inside M1 plus M2, which is also contained in R. Now, because M1 and M2 are maximal, and we know that M1 is not equal to M2, what that tells us is that M1 plus M2 is precisely the entire ring. This is useful because we can apply the Chinese remainder theorem from this. So, by the Chinese remainder theorem, what we can do is we can look at R mod the intersection, so M1, M2, and this is isomorphic to R mod 1 plus the direct sum of M2. This is a field because M1 is a maximal ideal. This is also a field because M2 is a maximal ideal. So you have that R mod I, because remember that this here is I, is isomorphic to a field, direct sum with another field here. And that's done. So the hard part is to realize that we already obtained this result here just by looking at the fact that M1 and M2 are maximal ideals, and because they're not equal, the direct sum must be precisely the entire ring. And once we have that, then the Chinese remainder theorem basically tells us the isomorphism. All right, and we have the proof here as well. Okay, so we've basically talked about rings for the entire time. We're going to talk about domains, and then we're going to move on to fields. So we're basically going to be looking at commutative rings, and we're going to be extending that notion of a commutative ring to a domain. And a domain is useful because we can start talking about factorization. So we couldn't really talk about unique factorization when we're talking about an arbitrary ring. But once we talk about a domain, we can start talking about nice ways to factorize elements inside your set. So we say that a commutative ring R is an integral domain if when you take the product of two elements being equal to 0, it implies that R equals to 0 or S equals to 0. And this is true for every R and S in R. So for example, if I had under Z, if I had something like 3 times 0 equals to 0, then either 3 must be 0 or 0 must be 0. And there's no other way. So if you take 3 times 1, 4 times 8, there's no way to obtain 0 without one of the elements being 0. And so this is what we mean by an integral domain. Cool. And yeah, so this is really convenient for us because we can apply the cancellation law. And what we note is that it turns out that if we take the quotient ring with a prime ideal, it turns out that the quotient ring forms an integral domain. So if you wanted to prove that an ideal is prime, you can also show that the quotient ring that you get forms an integral domain. Okay, so let's have a look at an example of an integral domain. I'll probably just do it here, just because it's not that much writing actually. So is the direct sum of Z and Z an integral domain? And the answer is no. So the reason for this is because we can take an element that's not 0, 0, 1. And if we take the direct sum of this, we get 1 times 0, 0 times 1. And then this is precisely going to be the 0 vector, or the 0 element. But we know that neither of them are 0. So this is not, this is not equal to 0. This is also not equal to 0. So this is not an integral domain because we have that R times S is equal to 0, but neither of them are 0. Alright, so we're given an integral domain then. So if we're given an integral domain, this might not necessarily be a field, but we know that every field is an integral domain. So one question that we might like to ask is there an associated field that comes with an integral domain? And the answer is yes, by the notion of a fraction field. So we're going to let D be some arbitrary integral domain, and we're going to define an equivalence relation as follows. So the equivalence relation is that two elements is related to another set of elements here if this equality holds. And then once we talk about an equivalence relation, we can start talking about the equivalence classes. And it turns out that if we look at the equivalence classes with the usual addition and multiplication operations, then it turns out that it actually forms a field. And this is what we call a fraction field. So the fraction field is really just the equivalence classes when we have this relation here, when we consider this relation here. So this might be useful because the fraction field itself is actually a field. And fields are fairly nice because there's a lot of factorization that we can do with a field. So for example, the fraction field of the integers, so if you look at the, we usually denote it as k, so k of an integral domain z is actually the rationals. Okay, and then we have some properties of fraction field. So if f is a field, then the fraction field of a field is precisely the field itself. If S is a subring of a ring, then the fraction field is a subring of the fraction field of the ring. And if R is a subfield of a field, then the fraction field of R is actually just a subfield of F. And remember that the fraction field of a field is precisely the field itself. Okay, so once we've introduced the notion of a fraction field, we can start talking about really nice factorizations. So this is what we call a unique factorization domain. And the idea or the motivation behind it is really just the fundamental theorem of arithmetic. Right, so every positive integer can be written as a product of primes. Well, actually, it's every positive integer can be written as a unique product of primes. And the uniqueness is not really true in the normal sense, but that it's unique up to associates. And we'll talk about what associates are later on. But the idea here is that in some rings, the notion of a unique factorization no longer holds true. So if we're looking at z adjoins square root of minus 5, we note that 6 factors into 3 times 2, both of these are primes, and 1 plus square root of minus 5 times 1 minus square root of minus 5. And it turns out that these two elements here are also primes. So the notion of a unique factorization no longer comes into play, because we can factor a number or an element inside this ring in 2 different ways. So what we want to do is we want to develop the theory so that this notion of a unique factorization still holds true. So some definitions before we start dealing with some theory behind unique factorization. So the first thing is to define a factor. So we define a factor in the normal way. So we take R to be a factor of S if there exists some T inside your ring, inside your domain, such that S equals to RT. We say that R and S are associates if we can find a unit such that R equals to S times U. And then we say that a non-zero and non-unit element R is irreducible if every factor of R is either a unit or an associate of R. And then we say that a non-zero and non-unit element P is prime if this property holds. So if we look at the normal factorization of the integers, right, 2 can be written as minus 2 times minus 1. Right, so it might seem like this is irreducible, but it turns out that minus 2 is actually an associate of 2, because we can express it as some element times a unit. So remember that under z, the only units of z are 1 and minus 1. So we can obviously write 2 as 2 times 1, we can write 3 as minus 3 times minus 1, but all of this doesn't matter because minus 1 here is a unit or an invertible element, and we don't really care about these elements here. So 3 and minus 3 are associates. Okay. Are associates. Okay, let me just rewrite this. Cool. And yeah, so what we can do is we can set some parallels between principal ideals and the factorization definition that we have here. So we say that R divides S if and only if the ideal generated by S is a subset of the ideal generated by R. We say that R and S are associates if and only if they are precisely equal. And we say that a non-zero non-unit element P is irreducible if the only principal ideals that contain the ideal generated by P is P and the entire ring or the entire domain. And a non-zero non-unit element P is prime if and only if the principal ideal generated by P itself is a prime ideal. Yeah. So what we can do is we can set some parallel definitions between factorization and principal ideals. And in this way, what we can do is we can set up some theory for principal ideal domains that we're going to be talking about. So in a commutative domain though, every prime element is irreducible, and the reverse is not necessarily true. There are irreducible elements that are not necessarily prime. Cool. Alright, so let's have a look at the definition of a unique factorization domain. So let's start off with a commutative domain. So that's the building block that we're going to begin with. And then we're going to add on some additional information about the commutative domain such that we get unique factorization. So to begin with, every element inside your unique factorization domain can be written as a product of irreducibles. Secondly, if you have that if you can factor the element in two different ways, then you have the same number of primes. So you obtain the same number of primes, and each of the primes are associates of each other, meaning that you can always express Qi as a product of Pi and an invertible element. So for example, what we can see here is 10 is the same thing as 5 times 2, but we can also factor 10 as minus 5 and minus 2. But it turns out that minus 5 and 5 are associates because they are scaled by minus 1, which is a unit. And similarly, 2 and minus 2 are associates, and remember that they scale by just a unit factor. Cool. So what we can do though is, instead of looking at specifically this dot point here, which can be a bit tiresome, we can look at an alternative definition, or we can look at an alternative result that implies this result here. So as it turns out, if every irreducible element is prime, then R is a unique factorization domain. And this should make sense, right? Because when we take an irreducible element, then the only way for this to happen, for us to maintain a unique factorization, is if the irreducible element is indeed prime. So if we have that result, then we also obtain unique factorization. Cool. Alright, so let's have a look at an example from the problem set 10. So let's start off with a unique factorization domain, and then what we're going to do is we're going to show that any two non-zero elements have a GCD. So we can define a GCD for any two non-zero elements. So R is a unique factorization domain. What that implies is that we can always write A in R in a way where we have A equals to P1 to the K1, P2 to the K2 up until Pn to the Kn, where Pi's are all irreducible. And similarly, if you take an element in your UFD, then what you obtain is a very similar thing. No, I should write K. All right. To P1 to the M1, P2 to the M2, and we're only going to be focusing on the primes that are related to each other. Pn to the Mn. So we can define the GCD of A and B to be precisely the product of all primes. So it's going to be I equal to 1 up to n of Pi to the minimum between Ki and Mi. And this is a well-defined operation. So given the GCD of A and B, we can define it to be the product of all primes that are in common with A and B. And then the power of these two is going to be the minimum between Ki and Mi. And this is well defined, and therefore every non-zero element, or any two non-zero elements, must have a GCD. Cool. All right. So we're going to show that this is not a UFD. So if you want to show that this is not a unifactorization domain, then what you can do is you can show that 21 doesn't factor uniquely into a product of irreducibles. So it turns out that these four elements here, 7, 3, 4 plus square root of minus 5, and 4 minus square root of minus 5, it turns out that each of these elements are irreducible. So meaning that if you try to express 7 as a product of two elements in this ring, you run into a contradiction. And the theory behind this is actually using what we call a norm. So you're using a norm function. What you can show is that 7. So if you have solutions to this, then what you can show is that 7 equals to something like a squared plus 5 b squared has a solution. But you can quickly show that this is false. This is a contradiction. So one way to note the contradiction here is, first of all, if we take, so A and B can't be 0. So if either one of them is 0, then, well, so if both of them are 0, then clearly you have 7 equals to 0, which is a contradiction. The second thing is, if A is 0, then the smallest number that you can obtain is 5, and then the second one is going to be 20. Well, it's going to be 5 times 4, which is 20, and that's already bigger than 7. So it turns out that if you set A to be 0, you can't have any solutions. If you set B to be 0, then you're solving 7 equals to a squared, which is not true. And so as a result, neither of them can be 0, but then if neither of them is 0, then you can't get 7 at all anyway. So as a result, this has to be, this has to have no solutions. And therefore, 7 is irreducible. And you can do the same thing with 3 as well. So you can show 3 is irreducible using this sort of reasoning as well. And you can do the same thing with 4 plus square root of minus 5 and 4 minus the square root of minus 5 as well. Cool. All right. So once we've talked about that, then we can talk about a principal ideal domain. So we've looked at the parallels between factorization and principal ideal domains. So we can now define what a principal ideal domain is. So let's consider a commutative domain. R is a principal ideal domain if every ideal is principal. That's pretty self-explanatory. And the reason why this is good is because we have a lot of these nice factorizations that come into play when we're talking about principal ideals. So R divides S if the ideal generated by S is a subset of the ideal generated by R. You have associates if they're equal, etc., etc. Okay, so it turns out that inside a principal ideal domain, every irreducible element in R is prime. So the way that you can show this is by looking at the previous results that we had. So if you consider some irreducible element P that's non-zero, then you can also consider the ideal generated by P. And because we belong in a principal ideal domain, the ideal generated by P is precisely going to be a principal ideal. So it's going to be the ideal generated by the single element P. But because we know that P is irreducible, then by definition, the only principal ideals that contain P are going to be the ideal itself and the entire ring. But what that means is that P is maximal, right? So P is maximal because there's no other there's no other ideal that contains P that's smaller than 1, or that it's smaller than the entire domain. And because the ideal is maximal, it's prime as well. And therefore, the ideal generated by P is prime, which implies that the irreducible element is also prime. And we obtain this result here. So one thing that's useful is that every irreducible element is prime. But it also turns out that we can factor any element as a product of irreducible elements. And with these two results, it's enough to conclude that a principal ideal domain must also be a unique factorization domain. So that's really nice because we have this inclusion now. We have that every principal ideal domain is a unique factorization domain. And we're going to be talking about this pretty soon as well, which is called a Euclidean domain. So we're going to show that this is not a principal ideal domain. So to show that it's not a principal ideal domain, all we need to do is we need to show that there is an ideal that is not principal. So let's consider the ideal generated by two elements. Let's just say 2 and x. It turns out that this is actually not principal. Because if it was principal, then we can find some element alpha in Zx such that the ideal generated by alpha is precisely the ideal generated by 2 and by x. But then by definition, alpha must divide 2 and alpha must divide x. But if alpha divides 2, then alpha must belong in plus or minus 1 or plus or minus 2. But if alpha is either minus 2 or 2, then alpha can't divide x. And the reasoning for this is very similar to one that we saw before. So if alpha was equal to minus 2 or 2, then the only way to get x is to consider half x as well. And it's not possible because we're looking at the integral domain of all polynomials with integer coefficients. So if alpha belongs in either 2 or minus 2, then alpha can't divide x. So alpha must be precisely, so alpha must be either minus 1 or 1. But then if that is the case, then 2x, so the ideal generated by 2x must generate the entire ring. But it turns out that we can't generate 3 from 2 and x. So 2x can't be the entire ring, and that implies that the ideal is not principal. And because we have an ideal in Zx that's not principal, it turns out that the polynomial, the set of polynomials, the ring of polynomials with integer coefficients can't be a principal ideal domain. Cool. All right, so we'll quickly wrap up the rings part by quickly talking about Euclidean domains, and then we'll talk about fields for the last half hour. So we've talked about two different types of algebraic domains. We've talked about a unique factorization domain, and we've talked about a principal ideal domain, and we gave some nice properties of both of the domains. We're going to introduce a new domain that's a bit nicer than a principal ideal domain, called a Euclidean domain. So a Euclidean domain is just a commutative domain with a valuation function. So it's a function that takes in the domain, the element in your domain, and it sends it to the natural numbers, and it satisfies these two axioms here. So if you consider non-zero elements f and g, if you take the valuation of f, then multiplying f by another element will never get you below f. So it will always be at least as big as f. And the second thing is, if you take f and you take a non-zero element g inside your domain, then what we can do is we can write it in a way that sort of resembles the Euclidean algorithm. So we can always write it as a product of g plus a remainder. And the remainder is never any larger in size than g. So that's a way that you might like to think about it. So an example of this would be to consider the Gaussian integers. So if you consider z adjoined I, and then you consider the valuation function, you take in a plus bi, and you send it to a squared plus b squared, then this is actually a Euclidean domain. And it's easy to show that this holds as well. Euclidean domain. All right, so some nice properties of Euclidean domains would be that every Euclidean domain is a principal ideal domain. And so as a result, every Euclidean domain must be a unique factorization domain. And so we obtain this subset here. So we obtain this inclusion, this chain of inclusions as well. So every Euclidean domain is a principal ideal domain, and every principal ideal domain is a unique factorization domain. So if you have a domain that's Euclidean, you automatically obtain a unique factorization domain, which is very convenient. So we're going to talk about Euclidean domain. So is this a Euclidean domain? Well, we've basically already clarified that this is not even a unique factorization domain, because we can factor 21 into two different products of irreducible elements. And therefore, this is not even a unique factorization domain, and as a result, it can't be a Euclidean domain. Cool. So the last part of this chapter is talking about Gauss's lemma. And Gauss's lemma is a very powerful statement because it talks about some really nice properties of polynomials. And we're going to be talking about polynomials a bit more for the last half hour. So we start with one definition. So we suppose that we're in a unique factorization domain, and we want to consider some non-zero polynomial inside the ring Rx. we say that f is primitive if all of the coefficients are coprime. So, for example, I think I'll give an example here later on, I think. Yeah, so basically the idea with a primitive polynomial is that every coefficient is coprime, meaning that the greatest common divisor among all of the coefficients is 1. So for example, if you're looking at zx, then 3x squared plus 1 is a primitive polynomial because all of the coefficients have GCD 1. But if you consider g of x, 3x squared plus 6, then you have that the GCD of the coefficient of x squared and the constant term is 3, which is not 1. Gauss's lemma tells us a lot about the product of these polynomials. So if you consider yourself in a UFD and you consider any two primitive polynomials, it turns out that the product of these two polynomials is also primitive. This is useful because this tells us a lot about irreducible elements in these rings. So the only irreducible elements in Rx are going to be irreducible elements of the underlying ring R, or they're going to be primitive polynomials of positive degree. And so these two are the only ways for you to have irreducible elements inside Rx. Cool. All right, so we're going to be talking about fields and the field extensions as well for the last half an hour. So recall that we've basically had some axioms for a ring. We're going to place a few more restrictions, a few more extra conditions on a ring for us to form a field. So the first thing is that we require that R is contains the multiplicative identity. So we require R to be a ring with identity. The second thing is we require R to be commutative. So meaning that we need to be in a commutative ring with identity. And lastly, every element or every non-zero element has a multiplicative identity. And then all of this together is called a field. And we usually denote this as F rather than with R. R meaning a ring, F usually meaning a field. So, to talk about extensions of a field, a way that I like to think about this is instead of going down, so you start off with a field and then you go down to a subfield, I like to think about it in the opposite direction. And it feels more natural talking about extensions in this way. So let's talk about, start with an example of what this actually means, and then we'll talk about it more formally. So let's start off with the field Q. And then let's consider what happens if I add, so what if I add square root of 2 into this field? I want to see what sort of elements I should add to Q so that I can get Q and square root of 2 together. So the first thing is that it needs to be closed under addition. So for example, 1 plus the square root of 2 needs to belong in this new field F. 2 plus square root of 2 needs to also belong in F. So in other words, A plus square root of 2 needs to belong in F for A in Q. So that's the first thing we want. The second thing is we want it to be closed under multiplication. So if we multiply any rational number with square root of 2, it also needs to belong in Q. For example, half square root of 2 needs to also belong in Q. And so as a result, if I combine these two results, then I require a plus b square root of 2 has to also belong Q. So that's the second thing. So we've introduced a plus square root of 2, but now we've also introduced a plus b times the square root of 2 into the mix. Well, I need to be able to divide by elements as well. So if I take, say, 1 plus square root of 2 divided by 3 plus square root of 2, that also needs to belong in Q. But if you rationalize the denominator, it turns out that this is actually of the form c plus d times the square root of 2. And c and d also belong in Q. So if I consider the field Q and I also consider adding in square root of 2, then it seems like the elements that I should add are of the form a plus b square root of 2. And this is precisely how we define this new field here. A, B inside Q. And so thinking about it this way actually helps with the idea of an extension as well. Okay, so let's look at the formal definition of an extension. So let's consider E to be a field, and E is contained inside F. So if F is a field, then we call F an extension field of E. So in the same way, Q adjoins square root of 2 is an extension field. Of Q. And we also say that the quotient, F quotient E, is a field extension. So those are just some notations and some definitions. So one thing that you might like to think about is, suppose that I have a finite number of elements inside your bigger field F. What we can do is we can look at E adjoined all of these things here. And we define this to be the smallest subfield of F that contains E, that contains alpha 1, alpha 2, and alpha n. And we call this extension simple if you can generate the field using just one element here. So for example, if I consider Q adjoins square root of 2, then what we're really saying is we want the smaller subfield of, say, R, such that we obtain Q, and we also obtain the square root of 2. And it turns out that the smallest possible field that we can obtain is just of this form here. So once we've defined an extension, we can start talking about algebraic and transcendental elements. So algebraic really comes from the fact that, we can define a polynomial. So this one, we can just define a polynomial. Here, so transcendental means not algebraic. So let F be an extension field of E, and we want to consider some element alpha inside your field. So we call alpha algebraic if alpha is a root of a non-zero polynomial with coefficients inside E. And we note that the first isomorphism theorem tells us that when we consider the quotient of P, we get precisely E of alpha is isomorphic to EX quotient P. And remember that P is irreducible, implying that the ideal generated by P is maximal. And then so as a result, when you consider this entire thing here, you actually form a field. If there is no polynomial with root alpha, then we call alpha transcendental. So let's have a look at this example. So we're going to find the minimal polynomial of alpha equals to this over q, and we want to explain clearly how you know that the polynomial you have found is irreducible. So let's go ahead and do this. So we want to find the minimal polynomial of alpha equals to the square root of 3 plus 2 root 2. So one thing you can do is, you can square both sides. So remember that you want to find a polynomial whose coefficients belong in, let's have a look, it's over q. So you want coefficients in q. So if we square both sides, then we have that, we get this. And then we can move the 3 to the other side, and we obtain this as a result. And we can actually write this as the square root of 8. And the reason why we might like to write it like this is that it's easy to see that the result that we get when we square both sides is 8. So we get that alpha to the 4 minus 6 alpha squared plus 9 equals to 8. So alpha to the 4 minus 6 alpha squared plus 1 equals to 0. And as a result, so you might think that this is actually irreducible, but you can actually reduce this even further. So it turns out that this can be factored into the following: alpha squared plus 2 alpha minus 1. So if you just expand this, then you get alpha to the 4 plus 2 alpha cubed minus alpha squared minus 2 alpha cubed minus 4 alpha squared plus 2 alpha minus alpha squared minus 2 alpha plus 1. So we can see that these two cancel, these two cancel, and so what we're left with is alpha to the 4 minus, so you get minus alpha squared minus 4 alpha squared minus alpha squared minus 6 alpha squared plus 1. So this is actually reducible, and then these two polynomials have coefficients in q. One thing you can notice is that this is actually a polynomial of degree 4, so you know that straight away it has to be reducible, because all polynomials in q are irreducible if they have degree 1 or degree 2. So you can tell straight away that this has to be reducible. Alright, so we need to figure out which one of the two the root belongs in. And then what you can do is you can just plug it into, you can plug in alpha into either one of these two, and you'll obtain, I believe, this one here. Another way you can do it is to realize that we can write alpha in the following way. So we can write it as 2 plus 2 root 2 plus 1. And notice that this is the same thing as saying root 2 squared plus 2 root 2 plus 1, which is root 2 plus 1 squared, which is root 2 plus 1, because it's positive as well. So if we get that, then we're just going to raise this. Then it's a lot easier to see what the minimal polynomial of this is, right? If you get alpha equals to root 2 plus 1, then alpha minus 1 equals to root 2. And so alpha minus 1 squared equals to 2, or alpha squared minus 2 alpha plus 1 equals to 2. And so what that implies is that alpha squared minus 2 alpha minus 1 equals 0. So you can show that this is actually the minimal polynomial as well. So if you define the following polynomial, so if you define f of x equal to x squared minus 2x minus 1, then clearly f of alpha equals 0, and you can check that no root, that there is no root inside Q. So the roots of this polynomial here do not belong in Q, and therefore this has to be irreducible. Cool. Alright, so the minimal polynomial, of alpha is f of x squared minus 2x minus 1. Cool. All right, so let's have a look at so once we define an extension, we can start talking about the degree of their extensions as well. So let's take an extension, and what we can do is we can view f as a vector space over E. And the degree of the extension is precisely the dimension of f over E. So if we take some alpha, which is algebraic, so remember that algebraic really just means that we can construct a polynomial that is minimal. Then we can define the degree of the extension field f of alpha as the degree of the minimal polynomial here. So in the previous example, where alpha was square root of 3 plus 2 root 2, the degree of the polynomial that we constructed was 2. And so f of alpha, so the degree of the extension is precisely 2. Cool. And what we can do is, if we have intermediary fields, what we can do is we can actually construct a tower of extensions. So if we look at the extension h over E, where f is an intermediary field, then we can construct an extension from h to f, and then from f to E. And it turns out that we obtain this relation here. Cool. So in order to find what these things are, it might be useful to know when polynomials are irreducible over a field. And this is where Eisenstein's criterion comes into play. So we're going to consider a polynomial, and what we know is that Eisenstein's criterion states that if we can find some prime p such that p divides everything except for the leading term, and the square of the prime does not divide the constant term, then f is irreducible over the fraction field k. So here, if we're looking at over a field instead, so if we're looking at a field, the fraction field k is precisely f. And this is a really nice way of looking at irreducibility. But just because you fail the criterion doesn't mean that f is not irreducible. You can still construct irreducible polynomials that don't satisfy the criterion, but if it satisfies the criterion, then f is irreducible over k, over f. So let's have a look at an example. So let's consider this, and we're going to find the degree of the extension given by theta. So one thing we can notice straight away is that if we consider just a portion of theta, namely if we consider just this portion here, it's easy to see that we can generate this element here, and we can generate this element here, and we can generate any intermediary elements here. So what we can do is we can write this as the following. So as a result, what we can do is we can construct Q of theta by Q of the pth root of p. So by our tower of extensions, we have that this result holds, right? Because if we consider the extension given by this, that has to be the product of the degree of this extension here times the degree of this extension here. And then both of these are integers as well. This is also an integer here. So as a result, we know that the degree of the extension given by theta has to divide the degree of the extension given by the pth root of p over q. And so we have this result here. But we can see that this here, the minimal polynomial of the pth root of p has to be x to the power of p minus p. And this is actually irreducible by Eisenstein's criterion, right? Because p divides everything except for the leading term, and the square of p can't divide minus p. So by Eisenstein's criterion, this is a minimal polynomial, or this is irreducible. And because the pth root of p is a root of this polynomial, it turns out that this has to be the minimal polynomial of the pth root of p over the rationals. And so what we get in the end is that this has to divide p, implying that this result holds. So either the degree of the extension is either 1 or p, but the degree of the extension can't be 1 because, well, theta, for example, is not a rational number. It's actually irrational. So it can't be that q adjoint theta is precisely q. And so what we conclude is that the degree of this extension is precisely p. So as it turns out, this is actually equal to the pth root of p over q. Cool. All right, so we can talk about splitting fields. So to motivate the concept of a splitting field, let's sort of look at an example. So let's consider the polynomial x squared minus 8. And let's consider this polynomial over two specific kinds of fields. If we look at this polynomial over the rationals, then f is irreducible, right? Because if we try to write this as a product of linear factors, then what we end up with is x minus root 8 and x plus root 8. But neither of these things belong in Q. So we can't write it as a product of linear factors. So as a result, this has to be irreducible over the rationals. But if we look at an extension field instead, if we look at this polynomial over Q's adjoint square root of 2, then certainly we can factor this into x minus 2 root 2 and x plus 2 root 2. And you notice that each of these coefficients actually belong in Q adjoint square root of 2. So this belongs in Q root 2, and this also belongs in Q root 2. So we can actually factor this into linear factors, where each of these polynomials belong in Q adjoint root 2. We call this field the splitting field because it basically splits your polynomial into linear factors. And we kind of reserve so what we would like to do is we reserve the smallest field to be the splitting field, because you can certainly have many different splitting fields, but there's only precisely one smallest splitting field. So let's have a look at the proper definition of a splitting field now. So a splitting field of some polynomial p is an extension field k such that p will split into linear factors. So in this example here, we looked at f being x squared minus 8, and we looked at the extension field q root 2, where we saw that q root 2 actually splits f into linear factors here. And we basically want to restrict ourselves to just the smallest field, and we call this the splitting field of P. Cool. A result by Kronecker states that we can always find a splitting field. So there is always a finite extension such that you consider any polynomial and it will split into linear factors. So what that tells us is that we can actually generate the splitting field as follows. So the first thing is that each of the elements here must belong in your extension field. And moreover, if the field f contains any of the roots, we don't need to consider them in our new field extension. Otherwise, we can adjoin the element so that the field extension now contains linear combinations of the root, and we just keep repeating it until we've included every root. And the resulting field is called the splitting field of f. So it's not too hard to actually generate the splitting field. And we'll look at an example where they ask you to find the splitting field of a polynomial. So let's have a look at this example. And we're going to also compute the degree of this extension. So let's do this. Okay. So let's have a look at the polynomial f of x equal to x cubed minus 11. And we're going to consider this over q. So let's first of all find the roots of this polynomial. So the first thing is we know the roots. So the roots of f come in the form cube root of 11. Cube root of 11 times some element here, and the cube root of 11 times this element here. So this element is the primitive third root of unity. Okay, so we can start to construct our splitting field. So first of all, we can see that none of these roots belong in Q, so we need to adjoin every single one of these elements. So let's start with this element here. So let's consider Q, which is a subset of Q adjoin the cube root of 11. So this will basically satisfy this root. So this root is now inside this this field here. But we see that none of these, so we see that none of these elements belong in Q adjoin cube root of 11. So we need to adjoin more roots here. So let's adjoin the second one. So we can see that we can already generate cube root of 11. So we don't need to consider this when we're adjoining new elements here. Instead, let's just adjoin this primitive third root of unity. And what we can see is that we can multiply these two elements together to generate this. So this here is satisfied, and also this here is satisfied as well, because we can take powers of this element here, and you'll still remain inside this extension field. So all of the roots belong in this extension field. So f indeed splits in cube root of 11 and this element here. And so what you can see is that this is actually the splitting field. Of F. Cool. We want to basically compute the degree of the extension now. So one thing we can see is that if we consider this extension field, we can consider this over the following. So over cube root of 11. And then we multiply that by the extension field generated by cube root of 11 over cube. So this is the tower of extensions that we saw earlier. So the minimal polynomial of this thing here over coefficients in this field actually come from the minimal polynomial of this. So the minimal polynomial, I'll probably write it in red. So the minimal polynomial of this element here is precisely going to be this. Because it's the third root of unity and it's not precisely 1. So it has to be this polynomial here. In other words, it's going to be f of x equal to x squared plus x plus 1. So this has degree extension 2. And this has degree 3. And so the entire thing here is 6. In other words, what we've concluded is that the degree of the extension is 2 times 3, which is 6. Cool. All right. And yeah, so here's some explanation in case you wanted to read it. And then the last thing we're going to talk about is just a really brief introduction to finite fields. So the idea with a finite field is that it's a field, obviously. So it's a field that contains finitely many elements. So the key point is that it has finitely many elements here. And it turns out that if f is a finite field, then the number of elements of your field is precisely a power of a prime. And the prime itself is called the characteristic of f. So the prime is the characteristic of f. And it turns out that if f is a field, then the set of units is a cyclic group of order q minus 1. And this is because in a field, every non-zero element has an inverse. So the only element that doesn't have an inverse is the 0 element here. Cool. So yeah, so the number of elements inside f star is going to be q minus 1. Okay, so let's do these two questions. So we're going to have two questions here, and then yeah. So we're going to prove that these two fields are isomorphic, but so these two rings are isomorphic. But it turns out that they're also fields. So let's have a look. So let's consider the mod 3z mod x squared plus x plus 2 and oh okay of x mod x squared plus 2x plus 1, I believe. Let me have a look. Plus 2. Okay, so the first thing we notice here is that the way that we're going to prove this this is true is by showing that these two things are irreducible over this field. So the goal here is to show that x squared plus x plus 2 and x squared plus 2x plus 2 are irreducible. And what that means is that the ideals generated by them are maximal. And what that implies is that the two rings are finite fields. Of 3 to the power of 2 elements. So that's the setup that we're going to have here. So the first thing is to show that x squared plus x plus 2 is irreducible. Remember that we're working in mod 3, so it's easy to check that these two are irreducible. So notice that 0 squared plus 0 plus 2 is 2, which is not 0. 1 squared plus 1 plus 2 is, so the 1 plus 1 is 2, that's 1, which is not 0. And 2 squared plus 2 plus 2. So 2 squared is 4, 6, 2, which is not 0. So this is enough to show that x squared plus x plus 2 is irreducible. The second thing is to show that x squared plus 2x plus 2 is also irreducible. So let's have a look. So what we're going to do is we're going to do the same thing. So 0 squared plus 0 plus 2 equals to 2, which is not 0. 0 squared, 1 squared. 1 squared plus 2 plus 2 is, so you get 1 plus 2, which is 3, so that's 2, which is not 0. And then you have 2 squared plus 4 plus 2, so that's 6, so that gets you 4, which is 1, so which is not 0. So this is enough to show that x squared plus 2x plus 2 is irreducible. So once you show that these two are irreducible, then what happens is that these two are fields of 3 squared elements. And it turns out that these two have to be isomorphic to F9. And so we have that this is isomorphic to F9, this is also isomorphic to F9, so they have to be isomorphic to each other as well. And there we go. So all you needed to show is that these two things are irreducible over this field here. Cool. All right. And the last question that we're going to do for this revision seminar is to classify all of these rings by their isomorphism. So let's do this. So this will be a really nice question to end off, because it also brings back a lot of the concepts that we saw earlier today as well. All right, so let's have a look. So let's have a look at these rings. The second one is F9, the third one is F3 cross F3. We're going to look at F3x squared. So x squared minus 1 and F3x mod x squared plus 1. Okay, so the first thing to look at is to look at these two things here. So notice that x squared plus 1. So the first thing is x squared plus 1 is irreducible. Over f3x. And so what that implies is that f3x quotient out x squared plus 1 is a field. It's a field of precisely 3 squared elements. And so what that implies is that this is actually isomorphic to the field of 9 elements. So these two are isomorphic. Okay, so the second thing we're going to look at is this and this. Yeah. So the second thing is we want to look at the quotient x squared minus 1. So notice that x squared minus 1 is the same as x minus 1 times x plus 1. And we can see that the ideal generated by x minus 1 plus the ideal generated by x plus 1, that equals to the entire ring. So that equals to f3. So it generates 1, and so as a result, it has to generate the entire ring here. So we can apply the Chinese remainder theorem. So by the Chinese remainder theorem, what we can say is that the ideal generated by the intersection, well, that's precisely the ideal generated by x squared minus 1. So by the Chinese remainder theorem, what we can say is that f3x mod x squared minus 1 is isomorphic to f3x quotient x minus 1 cross f3x quotient x plus 1. But then what we can say here is that these two elements here, so these two ideals are, so this is irreducible, and this is also irreducible over this field. So as a result, what you actually end up with is that this is actually isomorphic to a field of 3 to the power of 1 elements. So this is actually isomorphic to f3 cross f3. And so we've also defined another isomorphism here. So it turns out that these two things are isomorphic. Cool. So now we're going to show that each of the other isomorphisms, each of the other rings are distinct. So the first thing is Z mod 9. So this is actually an additive group of characteristic 9, characteristic 0. The other ones here are of characteristic 3. So you can tell that this has to be in its own group because it can't be isomorphic to any of the other ones here. So this is a ring, and the other ones here are at least domains. So what we can say is that this is by itself. So this one is by itself. We've proven that f9 and f3x mod x squared plus 1, they are isomorphic. But these two things can't be isomorphic, right? Because this takes an element, this takes a tuple, while this one is just an element, and there's no isomorphism between these two. So these two things are distinct from each other. And it also turns out that f9 and f3x mod x squared, they are also distinct. So they're not isomorphic. So the isomorphism classes that we have here are as follows. Z mod 9 f3x mod x squared plus 1 is isomorphic to f9, sorry. F3x mod x squared minus 1 is isomorphic to f3 cross f3. And f3x mod x squared is distinct. And so we have these 4 equivalence classes here. Okay. And that basically concludes the revision seminar. So good luck with all of your exams, and hopefully this has helped you revise for your exam. We'll be releasing all of the solutions and all of the slides in the next few days as well. So be on the lookout for that as well. And thank you everyone for coming.